Now on problem 2.1 from Wald's General Relativity, he asks us here to show that the overlap functions are infinitely differentiable, and thus completing the demonstration given in section 2.1 that the unit 2 sphere is a manifold. So before we actually get into solving the problem, let's just have a quick review of what actually is discussed in that section. So they talk about the idea of covering the unit 2 sphere with hemispheres and how many hemispheres this would take, essentially if they're open hemispheres that start from 0 of their respective coordinates. So with this, we can imagine attempting to cover the sphere with 2 hemispheres, the positive and negative y hemispheres. Oops. And in doing so, since these are open hemispheres, the circle where they meet is uncovered still at this point. So we can imagine putting 2 more hemispheres on, which meet along the positive, or not along positive, sorry, which meet along x equals 0. These are the positive and negative x hemispheres. And at this point now, most of the 2 sphere is covered, but we still have 2 points. Oops. 2 points. Why is my pen not working? One here and one over here where the circles meet that are uncovered still. And the idea is that if you use 6 hemispheres in total, so adding another 2 in the plus and minus z direction here, which I'm not going to try and do visually because that's going to be a nightmare. But then if you do that, you've used hemispheres to cover the 2 sphere. And the notation they use to discuss these hemispheres or to write them down is this. So a hemisphere is denoted O sub I plus or minus. And the idea here is that the I would be one of the coordinates, so like x, y, or z in our case, and then it would denote either the positive or the negative x, y, or z hemisphere. And we write that down like this. So we're going to list coordinates x1, x2, x3. Again, these could be x, y, or z. They're just coordinates, but we're going to write it this way. The coordinates belonging to the unit 2 sphere plus or minus x sub I greater than or not equal, greater than 0. So this is just saying that the hemispheres start from 0 and extend to the top of the sphere. And so to make it explicit, something like O plus x is the positive x hemisphere. Obviously O minus x would be the negative x hemisphere, and the idea then is that if you use all 3 coordinates, this set OI plus or minus covers S2. Now we can start talking about these mappings F. So each of these OI plus minuses can be mapped to an open disk D using projection maps. So we can imagine one of these maps F1, let's call it F1 plus, which maps from the hemisphere O1 plus to a disk. And this is defined by F1 plus acting on S2, X3, and we're going to map this now to a disk that flattens the coordinate specified by F1, so, or by F, sorry. So this is going to look like X2, X3, and etc. We can generalize this to, if this isn't 1, then you just pick the correct coordinate to remove. So now the overlap function, which is Fi plus or minus on Fj plus or minus, and this can be checked to be C infinity, which is what the problem wants us to do. Actually, just real quick, before we go ahead with that, I should also give an example of the inverse mapping. So the inverse mapping will take us, instead of going from a hemisphere to a disk, it will turn a disk back into a hemisphere. So if we let something like, let's say fy plus or minus inverse act on xz here, this disk, we will retrieve our sphere, our set of hemispheres, our hemisphere, sorry, not our set of hemispheres. We'll retrieve our hemisphere, where y equals 1 minus x squared minus z squared, just by the definition of the sphere, right? So now let's look at the overlap map acting on something arbitrary and see how this looks. So we'd have something like fi plus or minus on fj plus minus inverse, and we'll let this act on some disk x1, x2. So doing so, we'll keep the fi out front. And now the actual slot with which this goes into depends on what I was, obviously, but we're just going to use the middle slot here and say 1 minus x1 squared minus x2 squared x2. So all we're doing is bringing in a coordinate specified by I, specified by j, not by I, and using the definition of the sphere in terms of the other coordinates to say what that's going to look like. So now if we let fi act on this, there's a number of ways this can go, obviously. So if we assume that I is going to go after the middle slot, then we can get something back like this. Or if it goes after x2, we can get something like this. Or, I mean, I'm not going to write the square root for the last time, but something like this, obviously, and leaving the x2, etc. So it really just depends on what the what the I and the j are. But at the end of the day, that part is not so important, because in all of the cases, we notice that every single function here, whether it just be the coordinates themselves or the square root function, are all clearly infinitely differentiable with respect to any coordinate. So with respect to any coordinate. So therefore, overlap map is C infinity. And that's it for this part of the problem. Now in part B, let's see. He asks us to show by explicit construction that two coordinate systems, as opposed to the six used in the text, suffice to cover S2. So we can go ahead and do this. There are a number of more complicated ways to do this that I've seen online, but I'd like to keep things simple. So my solution is just this. We cover it with with hemispheres still. So we say O plus minus I is going to be something like x1, x2, x3 belonging to the unit 2 sphere. But instead of having the coordinates stop at 0, we're just going to pick one of them arbitrarily. So we'll say x1 in this case, plus or minus x1 is going to be greater than, let's say, -1, just some number that goes past 0. So the idea here is that if we have the sphere, if instead of having hemispheres that cover up to the center, we have one hemisphere that goes from the top down to like maybe here, and then another sphere that goes from the bottom up to like maybe, oops, I thought I had a circle, from the bottom up to maybe like here. Then if you color in the individual hemispheres, I mean, this is probably obvious at this point, but if you cover in the bottom hemisphere up to this line, cover a lot of the sphere. And then if you color in the top hemisphere up to the bottom line, you end up covering both of the open sections. So there's not this issue of the open sections lining up anymore, basically. So simply we've covered the sphere with just 2 of these, and that is it.